All right, we are going to discuss linear programming here in section 7.6. The process of linear programming has vast applications in the real world. We're going to see a couple of applications in this unit, but the first example is really just your typical math classroom example without any kind of connection to a real world problem. It's just let's learn the mechanics, let's learn the basics, and see how these things operate. So let's get right into it. Question says find the maximum and minimum values of, and then they give us this function, and it's written with a really weird notation. Weird as in just not something that you're totally used to. This function here, I like that feature. If I hold it, bolds out. So this function here, the f of x equals, f of xy equals x plus 2y plus 1. This is what we would call a function in two variable. Notice that it is f of xy, and then the function has both x and y in it. All right, so the whole reason why this notation has changed from our typical f of x to f of xy is because we have both x and y in the equation. Another way that you might see this is z equals x plus 2y plus 1. All right, this function is called the objective function, and we're going to deal a little bit more with that in a moment. But for now, it says for the polygonal convex set. A way to use some high-tech terminology here for something that really isn't that big of a deal. The fact that it calls it a polygonal convex set basically just means that the shape that this is going to create when you graph the constraints, the shape it creates is just a polygon. And it's polygon in nature where the shape that we're interested in is inside, so thus the convex word. But anyway, that terminology could have been left out of here completely. So what we've got here is a set of what we call constraints off to the right here, or off to the left side here. These are the constraints. These inequalities bound a region for which we choose values to plug in to our objective function here. All right, so that's a lot of high-tech words, again, for something that doesn't really have to be all that complicated. We begin by simply graphing each inequality on the graph. All right, we'll start out with these two simple x greater than or equal to 0 and y greater than or equal to 0, these vertical and horizontal lines that essentially cover the x-axis and the y-axis. This is x equals 0, and this one is y equals 0, right? And since it's greater than, it technically is telling us that we're shading to the right of that line and above that line. So it puts us in quadrant 1. All right, these two equations tell us that our region is in quadrant 1. I think every word problem we're going to deal with is going to have the equation in quadrant 1. These two constraints are very common. They are basically listed in every problem. All right, especially every applied problem, I should say. The second constraint, or the third constraint really, the 2x plus y, that they gave us some space here because that has to be worked out. We need to simplify this a little bit. In other words, we're just going to solve for y. I'm going to rewrite this negative 2x plus 12. Okay? And now if I graph that inequality, it gives me a y-intercept of 12, which is up here, and a slope of negative 2. So if I go down 2 and over 1, down 2 and over 1, I'm going to recommend, by the way, I'm sorry, I'm going down 2 and over 2. Let me back up. Down 2 over 1, down 2 over 1, looks like this. I'm going to recommend that while you graph these by hand, go ahead and draw as many points as you can, and then connect the dots. Draw all the points. You're going to see that that is very helpful along the way, because we are interested in some of these points along the way. And if you only drew, say, the y-intercept and then 1 point, yeah, you can get your line if you just have those 2 points. But you're going to miss out on some simple values rearing their head a little bit later down the way. All right, so draw all the points. You'll see why here in a moment. This is a less than or equal to. So I drew it solid, but less than means I'm going to graph under the line, so I'm shading in this region underneath. All right, we know now that we're kind of restricted into this triangle, but we have one more constraint. So let's look at that one. This last constraint says if I solve for y, 3y is less than or equal to negative x plus 21, which means y is less than or equal to negative 1/3 x plus 7. All right, so if I graph that one, I've got a y-intercept of 7, and then I'm going to go down 1 and over 3, puts me here, and then I just did that wrong again. Down 1 and over 3 actually puts me right there, and now you see why drawing these points along the way was helpful, because it gave me that intersection point. Down 1 over 3 again puts me over here, down 1 over 3 again, and I'm so far out of that shaded region that I am going to stop drawing the points and just draw my line. All right, so the line is going to come through like this, and since it is less than again, less than or equal to, I am underneath that purple line, which puts me in the shaded region here. Actually, let me use a slightly bigger highlighter. So my shaded region is this little, what they called earlier, a polygonal convex set. Basically this little four-sided figure here, polygon. All right, that's my shaded region. So that shaded region now is going to allow me to find what they asked for to begin with, which was the maximum and minimum values. Now here's the concept of all this. Your maximum and your minimum values will always occur at the vertices of your shaded region. Let me say that again. The maximum values of an objective function and the minimum values of an objective function, when given a list of constraints, will always occur at the vertices of the shaded region. Our vertices are here, 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 and here. We have 4 vertices. 1, 2, 3, 4, not in that order. You can start with 0, 0 as your 1. So if I do that, if my vertices are 0, 0, it looks like if I go clockwise here from 0, 0 to 0, 7 to, it looks like this point here is 3, 6, right? And then 6, 0 for my last point. Those are my 4 vertices. Now I calculate f of xy when x and y are these values. So I'm going to put 0, 0 in here. So I'm going to calculate f of 0, 0 is, if I put those two values in here, x is 0, y is 0, so these go away, and I'm left with just 1. If I put 0, 7 in, 0 in for x, 7 in for y, 7 times 2 is 14, plus 1 is 15. So f of 0, 7 is 15. If I put 3 and 6 in here, maybe you have to go off and you have to do a little bit of scratch work calculation. That's fine. F of 3, 6 is x is 3, and 2 times 6 plus 1. 2 times 6 is 12, plus 3 is 15, plus 1 more is 16. So this value is 16. And of course, if I put 6, 0 in, x is 6, y is 0, 6 plus 1 is 7. So this last one gives me 7. All right? Then it's just a matter of answering the question. The problem asks, what is the maximum and what is the minimum? Well, if I look at my answers, this one is clearly my minimum. Right? It's the smallest number. It's clearly the min. And then this one is clear, whoops, the third one is clearly my maximum. That's it. Problem solved. All right. So we use the vertices to find the max and the min of whatever objective function we are given. All right, let's move on. To summarize this process and what we just discussed, optimization is a process of maximizing. So it is a process that maximizes or minimizes a function, usually called the objective function, based on given conditions or given constraints. All right. One type of optimization, this is just one type because we do a whole other type in calculus and the other types and other types of in other methods of optimization in other mathematics-based classes. In particular, economics comes to my mind. One type of optimization is called linear programming, and that is what we are doing here. Linear programming. All right, a linear programming model consists of a system of linear inequalities. As I just said, those linear inequalities are called the constraints. And then what we refer to as an objective function. It is the objective function that we are trying to maximize and minimize. All right, so it's just some vocabulary here. So the procedure for linear optimization or linear programming. First thing we do is we define the variables. All right, you're going to see here in this this example down here that we are dealing with word problems in these exercises. So we have to define the variables of what we're given. Then we come up with a list of constraints. Remember that usually we'll use, as I said in the other problem, usually we will use, along with others, we will use x is greater than or equal to 0 and y is greater than or equal to 0. All right. We graph the system. You know, we come up with these constraints and we graph it. That's what we did up here. We found the graph. All right. We write an expression for what is being maximized or minimized. This, in other words, is we find our objective function. A lot of times we do that before we do anything else, to be honest with you. That might be step one, or at least the second or third step, not the fourth. Then once we have the graph and we have found the vertices, we plug the vertices into the objective function and we select the greatest or least based on what is being asked for. Okay, so with that process in mind, let's jump into this first example. Julia's lumber mill can turn out 600 units of a product each week. To meet the needs of her regular customers, the mill has to produce at least, got to pay attention to some of these key words here because we're writing word problems. So at least 150 units of lumber, 150 units of lumber, and 225 units of plywood each week. If the profit for each unit, of lumber is $30 and each unit of plywood is $45, then how many units of each type of wood should the mill produce in order to maximize that profit? And right there with those words, we are given, or we are told, what our objective function is. So I'm actually going to go all the way down to the bottom here, and I'm going to say, well, let me pause for a moment. We'll come back to that maximized profit, because before I write the objective function, it's important to make sure we have variables, right? So you'll see right below the variables were actually laid out for us. This will not always be done, okay? But here, there we are told that let L equal the units of lumber and let P equal the units of plywood, all right? So it made it easy for us because they labeled them. That was very nice. So if L is units of lumber and P is units of plywood, and then we are told that we are making $30 per piece of lumber and $45 per piece of plywood, then the total profit, which you can call capital P if you want, I'm just going to say T for total. The total profit is $30 per L plus $45 for each P, right? Per P. So that is my objective function. This function here is the function that I'm going to try to maximize, since they want us to maximize profit. This function is like, if I go back to the original problem, it's like the function we started with here. It's our objective function that we tried to maximize. We actually found the minimum and the maximum of this generic function. Well, now our function actually has a real world application or a real meaning to it because it's applied to this word problem. All right. So let's go back now. We got to find the constraints. All right. In this problem, we are told that they have to produce at least, that means at minimum, 150 units of lumber and 225 units of plywood. All right. And we are told in the very first statement that they can turn out 600 units in total every month. That was subtle, and I didn't really highlight it, but let's go back and let's pay attention to that. 600 units of product each week. So that tells me right there that the total number of lumber plus plywood is, that's at most, right? It said can turn out 600 units. Doesn't say they can do more than that. Obviously, if they worked less, they could do less than that. So the number of lumber plus the number of plywood has to be less than or equal to 600, right? Must be less than or equal to 600. Hopefully that makes sense. They can't do more, but they can do up to that. Then, if we look at this purple highlighted piece, they must produce at least 150 lumber. So lumber has to be greater than or equal to 150 because the least amount is 150. So we have to be greater than that or equal to it. And then plywood is greater than or equal to 225. They can produce at least 200. They have to produce at least 225 units of lumber or plywood. There are our constraints. We've got 3 of them. The first one is not necessarily into a form we like. Notice they've already drawn the grid for us. The x-axis is representing lumber, while the y-axis is representing plywood. P here, L here. All right. You could swap those. There is nothing saying that you have to do it this way. Believe me when I tell you, if you switched these, you'd have a little bit different math on this first problem, but you would still, if you did everything correctly, get the right answers in the end. Just pointing that out. But this one's laid out with lumber on the X and P on the plywood on the Y. So that means to graph this one, I want to solve for P. So I'm just going to write it as P is less than or equal to negative L plus 600. Hopefully that makes sense. All right. And we go to our graph. Let's graph this thing. It looks like my graph is unlabeled, right? So I got to decide on a scale that's going to work. Here, clearly, if I'm graphing this thing, I want at least 600 on my p-axis, because that's my p-intercept, right? So I'm going to say, let's go every 2 is 100. 100, 200, 300, 4, 5, and then this one up here is my 600. All right. So now with that, I got to do the x-axis. Let's continue. Let's say that every 2 is 100. 100, 200 here, 3, 4, 5, and 600. All right. So if I plot my first point at 600, again, that's because this indicates my y-intercept is 600, and then I go down -1. This is a little different. Pay attention here, because going down 1 for every 1 I go over means that if I went down 100, I would go over 100, right? If I go down 1 and over 1, then if I go down 5, I'm going over 5. If I go down 50, I'm going over 50. If I go down 100, from 600 to 500, I'm going to go over 100 units. So that puts another point here, and another point here, and so on. And basically, I'm going to end up all the way down at this -600 All right, so the first function graphs in a line like this. All right, and notice it is less than, so I know that I would shade under that. All right. Okay, moving on. The purple constraint says L, which is a vertical line basically. L must be greater than or equal to 150. So if I find 150, that is here, and I'm greater than or equal to that, so I am to the right of that line. All right? And then P must be greater than or equal to 225. All right, well, 225 is going to be kind of right through the middle of this. That wasn't quite through the middle. Let me see if I can try that again. That was better. Right through the middle, and I'm graphing above that line. Why is it above? Because it said greater than or equal to, right? So I am, you can clearly see now, I hope, that I am constrained to this region inside this little triangle. All right. These problems tend to get a little difficult for students, particularly, in a number of ways. And that's why they're a little time consuming. That's why we only got 3 examples in these notes. Because you're doing a couple of things. You have to come up with the constraints. You have to come up with the objective function. This is where students struggle the most, I'm not going to lie. If you can get these right, then you got to be able to graph it. You've got to be able to find the vertices once you do have it graphed. And then there's some algebra when plugging those vertices in here. A lot going on in these problems, I'm not going to lie. They can be difficult. In this one, it looks very clear to me that we have three vertices here, here, and here. If you didn't see those go on, again, right there, and right there. And our job is to find those coordinates. Well, not too tough because these values are set and they're pretty straightforward, right? This is 150 on the x, and it's sitting on the red line, so 225 on the y, or 150 on L and 225 on P. So this vertex is 150, 225. All right, moving on. This one up here, still at 150. It's still on the purple. 150 on the purple line, and it looks like 450 on the darker line. So it looks like black, but it's really a dark blue. So 150, comma 450. All right. And then this last vertex is the toughest one. It is definitely on the P axis at 225. But I need to know what it is on the L axis. And the truth is, if you want to calculate that, then plug 225 in for P. Right? Go back to that equation and plug that value in. If you said L plus 225 equals 600, right? If you plugged in 225 in here in order to find that coordinate, then you subtract 225 and it's going to be what you anticipated it to be by looking at the graph. I hope you did anyway, which is 375 over here. All right? If you subtract, you will get 375. Now, most people could look at the graph and say, oh, it's got to be 375. But if you were curious or it wasn't quite working, or more importantly, in harder problems where it doesn't seem to be quite as obvious, set values or set them equal to each other. Set the equations equal. In this case, you are technically putting P equals 225 in for P. All right, so now we have our 3 vertices. Now we're going to take each of those vertices and plug them into our objective function here. Plug them into the T, the total profit function. So if I do that, I'm gonna go ahead and say if you calculate those and you calculate them correctly, you're going to get, for this one, 14,625. For the second one, $24,750. For the third one, $21,375. And so it is pretty obvious here that the maximum, since we're trying to maximize profit, the maximum is at this value, the second value. So maximum profit, if you do 150 units of lumber and 450 units of plywood. All right, the question said, how many units of each should the mill produce to maximize profit? Well, if they do 150 units of lumber and 450 units of plywood, they will maximize profit, and that profit maximized will be $24,750. There we go. All right, let's do another example. This one's a pretty similar example, to be honest with you, but let's work it anyway. David's Carpentry Shop makes bookcases and cabinets. Each bookcase requires 15 hours of woodworking. All right, each bookcase requires 15 hours of woodworking and 9 hours of finishing. All right. Each cabinet requires 10 hours of woodworking and 4.5 hours of finishing. The profit for each is $60 on a bookcase and $40 on a cabinet. That problem right there, that statement right there, that sentence gave me my objective function here. All right. Rolling on here, they tell us that there are a total of 70 hours available each week for woodworking, and there are 36 hours available for finishing. And you can see now why I was highlighting in these specific colors and trying to color code stuff. All right. Because they gave us information about the bookcases and its woodworking, and information about the cabinet and its woodworking, and then they said the total woodworking hours available is 70. I need to group like units, woodworking hours, total woodworking hours. I need to group those together when I write my objective functions. My constraint, not my objective function, but my constraints. All right? And then you can see it's also 9 hours of finishing, 4.5 hours of finishing. I need to group that with the 36 total hours of finishing available. All right? And then it tells us in the last statement that we are maximizing profit again. So it's another maximize profit problem. All right. So my objective function goes with the green highlighted here. The total profit, I'll use P for profit here, is $60 per bookcase plus $40 per cabinet, per C. That's my objective function that I'm trying to maximize. Let's go back and deal with these constraints. Now there are 4 lines here. The question is why? Well, because you could make no bookcases, right? You can make 0 bookcases, which means the bookcases has to be greater than or equal to 0. Number of bookcases made. We're not going to have any negative bookcases, but they could make 0. You could make no cabinets, so cabinets is greater than or equal to 0. Remember at the beginning I said greater than or equal to 0, horizontal and vertical are going to be your constraints in most problems. It wasn't in our very last problem, but it usually is, these 2 constraints. All right, so if I move on, now I need a constraint that deals with the hours for woodworking. I can do 15 hours per bookcase plus 10 hours per cabinet, and the total has to be less than or equal to 70 hours. The maximum I have for woodworking is 15 per bookcase and 10 per cabinet. And then the maximum I have for finishing, I'm going to change the color here real quick. I just realized I was repeating colors. Okay, so the maximum hour I have for finishing is 9 hours per, finishing. 9 hours per bookcase and 4.5 per cabinet, and that must be less than or equal to 36 hours in total. There are my constraints. All right? Hopefully that works out. So if I want to graph these things, I'm going to have to solve a little bit. Well, we can graph the first two very easily, but let's solve these first. I want to solve for one of the variables, and if I notice my y-axis is in terms of c, and my x-axis is in terms of b, so I'm going to solve this equation for c. So I get 10c is less than or equal to negative 15b plus 70, which means c is less than or equal to negative 15 over 10 is 1.5, b plus 7. All right. In fact, instead of 1.5, let me write this as negative 3 over 2. Right? 15 over 10 is 3 over 2. All right, so I can see very clearly that my y-intercept for this problem is 7 and my slope is 3/2. I'm going to move this over just a little bit because I want the space to work on this y-axis. Oops. Okay, so if I do the same thing with my red equation here, I've got 4.5c is less than or equal to negative 9b plus 36. And this is a little more complicated, but c divided by 9 divided by 4.5. Notice that 4.5 is literally half of 9. So I'm basically breaking 9 into two pieces, right? So it's negative 2. Negative 2b plus 36 divided by 4.5 is conveniently 8. So it works out nicely. All right, so it is this equation. I want an oval. Daggone it. I'm just going to go with a square. Why not? All right, it's that equation and that equation that I am trying to graph here. All right, so I said equation. I really should have said inequality. All right, now that we've got our inequalities, we got them in the form we want, let's graph them. B is greater than or equal to 0. That's a vertical line basically here. C is greater than or equal to 0. That's a horizontal line on the x-axis. Basically, those two constraints, again, restrict us to quadrant 1. Okay? And again, greater than, so we are, in quadrant 1. Now, C, the third one, the woodworking, C is less than or equal to, I'm going to go 7 is, I'm just going to say each one of these boxes is 1. So 1, 2, and so on. 3, 4, 5, 6, 7 is here. I'm going to go down 3 and over 2, down 3 and over 2. All right, and that gives me, line looks like this. And it is supposed to be graphed under that line because of the less than or equal to. All right, so I'm constrained now to this little triangle. Let's do the last one. The last one says y-intercept is 8, and then the slope is negative 2. So down 2 over 1, bingo, I just hit, it looks like I just hit a vertice, or at least close to it. 1, 2, 3 over 2. No, that's a little bit off because that value should be, I think my line is slightly high on this other one. Let me redraw that line real quick. This line is just a touch too high. Oh, that doesn't look much better, to be honest with you. All right, I'm just going to leave it. This vertice goes down 2 and over 1, and then down 2 and over 1. That's the vertice. This point right here is not quite on the line. My line is just a hair up. That point is not on the line, but this one is. Okay, just pointing that out. All right, then I go down 2 and over 1 again, and I'm here. Down 2 and over 1, and I'm here. All right, and so here, if I draw my line, you can see it better now that this red line is drawn. The region that I am constrained to is here, because I have to graph under that red line also. All right, so if I zoom in a little bit, you can see I've got this little wedge here is not included, and then this little wedge here is not supposed to be included. And my vertices are, actually let me do highlighting here, are here, 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 and then of course at 0, 0. All right? So those 4 orange highlighted pieces. So those are my 4 vertices. Obviously 0, 0 is 1, but since we're trying to maximize, and that 0, 0 is worthless. It's not even, I know that's not going to be the value. I've got another one at 0, 7. That's this one here. I've got another one at, it looks like 2, 4. That is here, right, at this value, 2, 4. And then I have one at, it looks like 4, 0. 1, 2, 3, yeah, 4, 0. 4, 0. And that is this one here, right? 1, 2, 3, 4, 0. All right, so those are my 4 vertices. Now that I have those values, I'm going to take each of these points and I'm going to plug them into my objective function here to calculate profit. So if I do that, I'm going to get obviously 0 here. If I put 0 in for bookcases and 7 in for cabinets, I get $280. If I make 2 bookcases and 4 cabinets, or whoever this is, I keep saying David. If David makes 2 bookcases and 4 cabinets, he's going to make, again, $280. And if he makes 4 bookcases and 0 cabinets, he makes $240. Again, I'm getting these values by taking 0 and 7, 2 and 4, 4 and 0, and so on, and plugging them in to this objective function. So in this problem, he's actually going to maximize profit in either of 2 ways, either here or here. All right? So it can maximize his profit if he produces 0 bookcases and 7 cabinets, or if he produces 2 bookcases and 4 cabinets. All right? And there we have it. Example 2 is complete. All right, one final example here. Zoe's Leather Company. I'm going to try to roll through this quickly. Zoe's Leather Company wants to add handmade belts and wallets to its production line. Each belt nets the company $18 in profit, and each wallet nets $12 in profit. Right off the bat there, we are kind of given the objective function. You'll see that this is a very repetitive problem. $18 in profit per belt, and $12 in profit per wallet. Both belts and wallets require cutting and sewing. Belts require 2 hours of cutting and 6 hours of sewing. Wallets require 3 hours of cutting and 3 hours of sewing. All right, let me go back and break that down. Belts, 2 hours of cutting. Wallets, 3 hours of cutting. Total cutting. The cutting machine is available for 12 hours a week. All right, cutting is available for 12 hours. Maximum cutting basically is 12 hours. And then, actually let me use a different color. And then 6 hours of sewing per belt and 3 hours of sewing per wallet. And the sewing machine is available for 18 hours a week. All right, what mix of belts and wallets will produce the most profit within the constraints? If I'm being honest here, if I were you, I would pause the video now. I would try this question on your own. Completely do it on your own, and then go back and see. Now that I've done 2 examples for you, go back and see if you've got the answer right by watching the rest of the video. All right, so pause now and try it. All right, we are trying to calculate the profit. So my profit objective here, I'm sorry, let me back up a little bit. I didn't talk about the variables. B and W. B represents obviously the number of belts, while W represents the number of wallets. All right, so with B and W, number of belts and number of wallets, I'm told that I'm going to make a profit of $18 per belt and $12 per wallet. All right. Well, I could make 0 belts or more. I could make 0 wallets or more. Zoe could make, I should say. So I have the two constraints that constrict me to quadrant 1. That is here and here. Again, I feel like that's pretty obvious that we're in quadrant 1. Then I have 2 hours of cutting available for belt, or sorry, it takes 2 hours to cut a belt and 3 hours to cut a wallet, and I have 12 hours total available. So 2 per belt plus 3 per wallet must be less than or equal to the 12 I have total. All right, there's my equation, or my constraint for cutting. And then I have a constraint for sewing. 6 per belt plus 3 per wallet is less than or equal to a total of 18 hours there for sewing. So if I want W on the y-axis, then I'm going to take each of these constraints and solve for W. All right, if I solve this one, and 3W is less than or equal to negative 2B plus 12, and W is less than or equal to negative 2/3 B plus 4. And if I take the other one, 3W is less than or equal to negative 6B plus 18, which means W is less than or equal to negative 2B plus 6, right? All right, so I've got the two red ones already drawn. Let's draw this purple one. I've got a y-intercept of 4, and then I would go down 2 and over 3, and down 2 and over 3. So there is the purple constraint for number of hours of cutting available. And then I'll do the same thing for the blue line, except here I've got a y-intercept of 6. And I'm going to go down 2 and over 1, down 2 over 1, down 2 over 1. All right. I think I did that right. Start at 6, down 2 over, yeah, okay. You'll notice here that we have an issue. By the way, these are all, the red lines keep me in quadrant 1, but the purple and blue lines keep me under them. So my area is here. And I was going to say, we have an issue with one of the vertices in this problem now. It is not so obvious. All right, this one here is not obvious. We have to find that value. We need to know where that intersection occurs. We can find the others. Those are pretty simple. We've got 0, 0. That was here. We've got 4, 0. I'm sorry, 0, 4, I should say. We've got 0, 4. That was this one. And then we have this one all the way, this one right here, which is 3, 0. I'll put that as my last one. What we don't have is this one in the middle. How do I find it? I set my two inequalities equal to each other. The answer is here at the bottom, by the way. But let's set them equal. Let me show this. I'm going to say negative 2/3 B plus 4. Right? Again, why am I setting them equal? Because the blue line and the purple line are intersecting. They are equal at that point. So equals my blue line, negative 2B plus 6. And I can solve for B. Once I have B, I can find W. All right. So let's add 2/3. No, let's add 2. So if I add 2B, if I bring this 2B over and join it with those B's, that gives me basically 1 1/3, which is 4/3 B. And then if I subtract the 4, I get 2 over here. And now if I multiply by 2/4, B is equal to, multiply by 3/4. Then B is equal to 6 over 4, which is 3 over 2, right? 3/2. So if B is 3/2, then let's say W, yeah, that's easier. Then W would equal negative 2/3 times 3/2 plus 4. I'm just taking that 3/2 and plugging it in here. I could plug it in here also, but it actually works quicker and easier here. So if I do that, I get negative 1 plus 4, which is positive 3. All right, and that is pretty obvious because we can look at our y-axis and see, or our w-axis, and see that it's intersecting at 3. All right, so 1.5 is the b value. Didn't quite look like it. Looked like it may have been 2/3, or 1 2/3, but it's actually 1.5, and then 3. So that's the other intersection. 1.5 on the b and 3 on the w. All right. If you plug those values in to the objective function, you will get, obviously, $0 if you make nothing. You'll get $54 if you do, nope, I'm sorry, that one's wrong. You'll get $48 if you plug this in, 0 and 4 into here. You'll get $63 if you make 1.5 belts and 3 wallets per week, and you'll get $54 if you make 3 belts and no wallets. So it is maximized if you make 1.5 belts and 3 wallets, right? There's our maximum. All right. Hopefully that makes sense. There's a lot going on. Practice makes perfect, or makes better anyway. Good luck. Thank you.